Okay, so last time we were talking about virtualization. There is a handout that I will put out on Moodle today that will cover that topic because it's not in the book, so keep an eye out for that. We will switch gears today, talk about code and process migration. Okay, but before we start, I'm going to continue the parable I had related last time. Okay, so remember the rabbit and the fox. So we'll have a part two. Okay, this one is called The Lion and the Fox. So we continue the story from where we left off last time. So this time there's a lion sitting outside the cave. Okay, and the fox comes along looking very gloomy. And then the lion asks the fox, saying, "What's wrong? Why are you so gloomy?" The fox says, my fine wristwatch has stopped working, so I can't tell the time." And then the lion says, "Let me fix it for you." And the fox looks at the lion and says, "You have big paws. This is a very fine instrument. How can you ever fix such a fine instrument?" And the lion says, "Don't worry." And he takes the watch inside the cave. Sometime later comes out and the watch has been fixed. So then a short time later, a wolf comes along, and the wolf is also looking gloomy. And then the lion asks, "So what's wrong?" The wolf says, "I'm trying to write on a grant proposal, but my laptop disk drive crashed and I cannot work anymore." And then the lion says, "I'll fix your laptop for you." And then the wolf says, "How could you possibly do that? Because it's a fine instrument. You have fat paws. You couldn't possibly fix it." And then the lion goes inside with the laptop, comes out a short time later, and the laptop is fixed. And then a short while later, the lion goes inside, and inside there is a flock of rabbits sitting with fine instrument fixing all the items. So the moral, what's the moral of the story? So in this case, the lion is the advisor, and the rabbits are the student. So the moral is, it doesn't matter what the advisor knows, it really matters what the students can do. Okay, so we will continue from last time. So we were talking about virtualization. I forgot to actually show this slide. It was the very last one. Somehow I didn't remember it was the last one. So in the context of OS virtualization, there is a system called PlanetLab, which is a distributed set of machines that universities have put up to do research experiments. So anybody who wants a machine to do some research experiments or do networking measurements can get an account on PlanetLab and get accounts and get access to a set of machines that are distributed, because there are many tens of universities that participate in this lab. And the way it works is it uses OS level virtualization. So when you get an account, you get what is called a slice on the server. And that slice is essentially a small virtual server, which is essentially OS level virtualization. So any processes you run are isolated from other experiments that other researchers may be running there. So you basically can have multiple users using the machine at the same time. Each slice is isolated at a resource level. Processes are not visible to one another and so on. So you do your own experiment independent of what else may be going on. So that's an example of using OS level virtualization. In the cloud context, it's all hardware virtualization and hardware virtual machine. But here is an example where they decided to go with OS level virtual machines. And the reason for that is these machines that people have contributed to this lab, they're not very powerful. So they cannot run a lot of hardware virtual machines, but OS level virtualization is a lot cheaper. You don't end up running multiple kernels, you're simply providing resource isolation. So it's more efficient, you can support more experiments on the same hardware. Okay, that was the reason they went about with OS level virtualization. Okay. So that's just an overflow from last time. As I said, today we'll talk about code and process migration. This will just continue the discussion on processes and threads, and this will be actually the last topic that we will cover in that entire set of lectures. So we'll talk about what is this migration, why is it useful to study. We'll talk about how to implement process migration. Okay? And then I'm going to provide some details of forms of migration as they exist today. Okay. So if you remember the discussion from 2 lectures ago, when we were talking about distributed scheduling, that was that Friday makeup class where I said we had covered this concept of distributed scheduling. In that context, we said processes can move from one machine to another. I said we'll come back and discuss that because that's not something that a standard OS supports. You can't just start a process and tell the OS now move it somewhere else. Most operating systems do not support that functions, but there are some that do. Okay, and those are the ones that support migration. So look at that in a little more detail. So there are many reasons to do it. One is performance, another is flexibility. We'll come to those in just a moment. But let me distinguish between the two kinds of migration we are interested in. Okay, one is actually real process migration, okay, which is also referred to as strong mobility. Okay. So this is a process that's actually running on a machine. You can move that process to another machine, okay, and then it continues executing on the second machine. Okay, it's a real process, real executing process that has moved over and continues to execute. Okay. This is referred to strong mobility. Now contrast this to what is also referred to as weak mobility or code mobility. So in code mobility, you don't move a process, but you move a program and then start executing the process. You move code over and then execute that code. It could be a script, it could be actual program, it doesn't matter, but you're moving code and then the code starts executing as a new process on that other machine. Okay. So here the code is moving. When you move a process, clearly the code for that process moves with it. Okay. This is binary code in this case, and as well as the process state. In code migration, is as simple as moving a script over or just copying some code over and then starting to execute it. Okay? So this is far more prevalent even today. Okay? There are examples of this. For instance, if you think about Java applets that you can download into your browser, that's some code that the server has shipped to you. It's executing as a Java applet inside the browser, as an example. You could also think of filling a web form and sending that over to the server. Okay? Your browser then actually sends a query. Okay? The form includes data, and you construct a query and hand it off, and the server will execute that query, which is typically taking the form and inserting a record into a database. That's also code that in this case the client has sent to the server. So there are many examples of code migration. Process migration is not very common. Okay, there are systems that do that. There are two that are mentioned here. One is called Condor. This is a batch scheduling system that I also mentioned as a case study 2 lectures ago, where you have a collection of machines. You can submit jobs to the machines. Jobs are assigned to idling machines. They run. The machine needs to be taken back by the user. The job moves. Okay? That's handled using process migration. Okay, DQS is distributed queuing system. It's another batch scheduler that supports process migration. Okay, now here are some other examples of code mobility. Okay. So this one is actually configure on demand. Okay. So there are many operating systems now that allow you to plug in a piece of hardware to your machine. Okay. You don't need to have a driver for that hardware pre-installed. When you actually plug in the hardware, the OS will scan the hardware, determine what kind of hardware it is, and either offer to download a driver from a driver repository or tell you, saying there's no driver. Should I go look for the driver on the internet, and it will go search some repositories and download the driver. Okay? You can have either a driver repository or you can just go search for it and download it, and then you insert it into the OS and the hardware starts working. It's another example of code migration. This is also often used in the database world, where your database drivers, they're not hardware drivers, they're software drivers that allow you to talk to a particular database. Okay, if you've heard of JDBC or ODBC, those are examples of database drivers. There are many others like that. Okay, some database systems are written to download the driver on demand, so you can actually talk to a particular piece of database, a particular database server. So that's more flexibility, because you don't need to have every possible piece of software or drivers pre-installed on your machine. Okay, you download them on demand and you get the code on demand. Any questions on this so far? Okay. So now we'll talk a little bit about various dimensions that arise when you do migration. Okay. So first thing is, when we talk about a process and a process migrating, we mean that all of those things that are listed there are going to migrate. So a process will be assumed to have some segments. Okay? There's a code segment that consists of the binary code for the process. That's the actual code that is being executed. There is a stack segment, there's a heap segment, that's where the data for the process is stored. Okay? So here, the execution segment is basically the stack. Your resource segment could be, you may have open files and things like that. Okay? So essentially a process will have at least 3 segments, maybe more. Okay? Code, heap and stack, and then you have resources and other kinds of segments, shared libraries. When you move a process, you have to move all of those things, okay, from one machine to another. That's what we will assume. We'll see how to do that in just a little bit. Okay, but that is what we mean by process migration. Okay. In code migration, we are only talking about moving code. Okay, this could be a pre-compiled program. Okay, that's a binary. It could be a script. It could be a Python script that's interpreted. It could be a Java jar file. It doesn't matter what form it is in, whether it's source code or intermediate code or binary, but you are moving code over. Okay? And then you invoke a process that starts executing that code. Okay? That is basically weak mobility. Okay? So what is actually moved from one machine to another in either strong migration or strong mobility rather, and weak mobility are two different things. Okay? The other dimension is who initiates the migration. Is it the sender or the receiver? In sender-initiated migration, as the name suggests, the sender, which is the one that sends the code, is going to initiate it for you. Okay? Example of this is query being sent off to a database server. You construct a query, so you have the code, you send it off to a database server to execute, possibly over a network. Okay? That is sender-initiated code migration. Okay? Receiver-initiated is you are actually asking the entity that holds the code to send the code to you. Okay? Java applets, Flash applications are good example. Okay? The code resides on the server. Your browser can actually download the applet and start executing it. Okay? Same with JavaScript code in HTML. The code is on the server. The receiver is the browser. The browser is initiating the migration. Okay? Any questions here? So that's pretty high level. So, and the last point is who executes the migrated entity, okay, or how it is executed. In code migration, you start a separate process. In process migration, you will basically move the process over. There are 2 ways to do this. Okay, one is referred to as remote cloning, where you clone the process. You create a mirror image of the process. Okay, that's called cloning. Okay, and then you continue executing the latter process and stop executing the former process. You could, after cloning, actually continue executing both, but in migration, you will just clone and then stop one of the copies. Okay, or you can use real migration, which is you don't clone, you're simply moving the state and then registering the address space with the new operating system kernel as a new process. Yeah, so go ahead.
When the migration is initiated, the process is of course stopped, right?
And the migration is initiated, is the process stopped? So that's a good question. I did not actually say how this process of migration is going to work. Okay? When we talk about virtual machine migration in just a moment, we will see that you do not need to stop the process. You can actually continue executing the process, and the migration is happening while the process, in that case the virtual machine, not the process, is being migrated. Right? So clearly one way to migrate is you pause. Okay, so then the process is not executing, you move all of its state over and you resume. That's the simplest way. But that involves taking a downtime. The process stops running while the process it's migrating. Okay? Another way to do this is what is referred to as live. Process continues to run. Okay? It potentially will keep modifying its memory at this state, and yet you can migrate. We'll see how to do that in just a little bit in the context of virtual machines, not processes. Okay? So these are the various dimensions we just discussed. Okay? So this is, depending on which options you pick, you will end up with one point solution in this entire space of how migration is going to work. So you can have weak or strong process migrating or code migrating. Within each, you can have sender initiated or receiver initiated. Okay, who initiated the migration, and then what tech mechanism are you actually going to use? Are you going to migrate the process, clone the process? Here you have an option of when you move the code over, do you start it in a separate process from the one that downloaded the code, or you just start execute it in the same process? Okay. Java applets typically execute in the context of the browser. You downloaded the code, it's executing inside the browser. It didn't start a new process. But you can think of scenarios where you download the code and you fire off a new process to execute it. So that's basically execute in the target process or separate process are two options there. So that's a very generic discussion of code migration. We'll now start looking at more specific. Okay, so as I said, you have these various options and you will end up with a point solution. Each of this is basically a point solution saying what are the options or dimensions you picked to design the migration system. Now the most important, or not important, the difficult part of migration is what happens to resources that are being accessed by the process. Okay? When the process moves, how are those handled? Okay, when we talked about process migration very briefly, 2 or 3 classes ago, I mentioned a process may have a network socket open. The process may be communicating over a network. There's a network socket. Network sockets are bound to IP addresses. Okay, basically, the way socket works is you have an IP address and a port number. Okay, the IP address is specific to the machine, not the process. Okay, so if you simply move the process over to a new machine, okay, it is going to now execute on a machine with a new IP address. If it had a socket connection open, all the packets from the destination will continue to arrive at the previous machine because the socket is bound to an IP address, not to the process itself. Okay? It is bound to a port number and an IP address, but the IP address is still the old one when the connection was open. Okay? So now your connection will break, very simply put. Okay? If you just move the process blindly, how do you handle that? Okay, another simple scenario is you are accessing a local file. Okay, even more common than network connection. Your process has just opened a file and it's reading or writing to the file. The file sits on the disk. Okay, you move the process over. Okay, the file is still on the machine. Okay, now if it just tries to access a file with that name on that machine, it's going to get an error because the file is on the previous machine. Okay. So you have to deal with resources in some reasonable way for the migration to work. Otherwise, what will happen is you can only move processes that either don't do file I/O or don't do network I/O. Okay, that's a very small and restricted class of processes. Okay, nevertheless, a useful class. Okay, you may run simulation jobs that just do some computation and output a result. They're not accessing file. They're not doing communication. Those processes you can move. Okay? But any more complex process that may be either doing file I/O or network I/O, or even worse, accessing some hardware on a machine, okay, will not be able to function if you just move it. Okay. So how do you deal with resources? And that's really the question that we are going to discuss in a little more detail. Okay. So the first thing we'll use the term resource in a generic way. So it doesn't matter what kind of resource is it. Is it a file? Is it a socket? Is it a hard piece of hardware like a printer? We will abstract out and just talk about resources more generically. Okay. So first thing we will say is the way you deal with resources depends on what kind of resource it is. And we will have 3 types of resources. Okay, there's a resource that you will access by identifier, there's a resource that you access by value, and there's a resource that you access by type. Okay, and then basically what that means is depending on what category the resource falls into, how the process accesses those resources can potentially be different on different machines. So when you access a resource by identifier, okay, you are accessing a particular unique resource and that resource only. You can't substitute that resource with something else. Let's say it's a URL. Okay? You are accessing a web page. Okay? You can't just substitute it with some other web page. The process wants that web page, it needs to be given that web page. Or it could be a specific type of a file. Okay? So that's those are resources that even if you move from one machine to another, you still have to access that resource that the process is trying to access. You could have resources that you can bind by value. Okay. There the coupling is weaker. So let's say you want to execute on a JVM, okay, of Java 2, let's say. Okay. When you move from one machine to another, so long as Java 2 virtual machine is installed, you don't necessarily need the old file. You can just rebind to whatever copy exists locally and execute them. Okay. Same way, if you need a C library to run, okay, and it's a specific version of the C library, the same C library is present on the new machine. You don't need to move it or anything like that. You can just rebind to the copy that's available there. Okay. So here binding is by value Okay, in the previous case, when you have identifier, you can't change it. If you say I want a particular URL, you can't substitute it even if there's something else that may be somewhat related. Here, you can substitute one copy with another on different machines. And the last one is even weaker binding. It's by type, where you may have things like printers. Okay. So you just want to print. Okay, on one machine one, the first machine, maybe it was an HP printer. Okay, you are not even going to say I need an HP printer on the second machine. Any printer will do. Okay, so long as it's, let's say, color printer or a black and white printer. Okay, so the binding is even weaker. You can even substitute across types. You're not even going to say I want precisely that model. Okay. So what this discussion should tell you is not all resources should be handled the same way. Some resources allow you more flexibility when you move a process than other resources. Okay, and we will use that flexibility in designing more efficient ways to migrate a process. Okay, then that's one sort of dimension. The other dimension is, suppose you have to move resources. Okay, what is the cost of moving those resources, and when would you do it or not do it? Okay? The simplest one resources are what are referred to as unattached resources. Those resources can move from one machine to another if you want to move them for some reason. Example could be a file. Okay? If you want to move a file with a process, move that file. Okay? That's an unattached resource. Okay? Fastened resources are resources that can be moved, but the cost of moving them is high. Maybe it's a large file. Example could be a database. You can have a 1 gigabyte database. You could move it with a process that may be accessing the database, let's say. But the cost of moving it is much higher than moving a smaller piece of data. And then there are fixed resources. These are resources that you cannot move, okay, with a process. Example may be hardware devices attached to a machine. Okay, simply because a process moved, the printer can't move with it, at least not automatically. So those are fastened resources that we will not be able to move. Socket endpoints fall in that category. They are attached to an IP address. IP address is assigned to a machine. So you can't just move a socket. Okay, you'll have to do something extra to deal with that situation. Okay, so this is another dimension that tells you what cannot be moved and at what cost. Okay. So now with that discussion or background, let's try to ask the question, depending on what kind of binding you have and what kind of cost you incur, what would you do in various scenarios? Okay. So let us say you have a resource that is bound by identifier. It's a URL and it's unattached. Okay. In this case, you will have to move that resource. Yeah, if it's unattached, that means you basically you can move it from one machine to another. If it is fixed, you need to provide a remote access to that resource. Okay. There are only two basic things you will do. Okay. Either move it or continue to allow access on the old machine when you move a process. Okay, so those are the two scenarios you will have in front of you. Okay, when a process moves, any resources that it was accessing will either move with the process or the resources stay there, but the process continues to access those resources over a network. Okay, so the only two options. Otherwise, the process will break if you don't give it access to the resource that it was accessing. It will crash. Okay, so to continue to give it access, you move the resource if you have reasonable costs. Okay, or you allow remote access. Yeah, so you will see that fastened resources, okay, these are resources that can be moved with a high cost. Typically, you want to give remote access. GR stands for, I should mention what the term. GR says established global system-wide reference. It's a fancy way of saying you have remote access to the resource. You can access it over a network. Okay. MV just says move the resource. CP says you can copy, make an extra copy, and then you have RB, which is rebind, saying don't move it, just find something equivalent on a local machine and give it. So that was the example of a printer. Right? If you have a local printer, you don't even need to send the print job remotely to the old printer. You can just rebind to a local copy. Okay, so those are the four options we have. Okay, so you will see that there are, for each of these you can do multiple options, but the most preferable one is shown as the first choice, and then whatever other options are available are shown in parentheses. And that's a table from the book. So you will see fixed resources basically either provide remote access, or if the binding is weak, which is it's a type binding, you will rebind. If it's a printer, you will just rebind. If there's other two kinds of resources, you will basically provide remote access. Okay. In unattached, you basically either move or copy. And if it's a very weak binding, then you can of course rebind to a resource. Okay. And if it's fastened, essentially means you can move it at a high cost. Typically, then you don't move it. Okay. You try to provide remote access to the resource. And then here, by type, always if you can rebind, you always rebind. Okay. Because type just says weak binding. If you can substitute one resource for another, do that. Okay. Any questions here? Okay, so that's based. So now, as a system designer, okay, when if you're designing a system that allows you to move a process, you have to make these decisions, saying what kinds of resources could a process that I'm trying to move access. How do I deal with it? Okay, should I move it? Should I copy it? Should I provide remote access to it? Should I rebind to an equivalent resource on the new machine? And you have to implement that in your system. The process will not do anything. The process is simply being moved. Your system that is moving the process will have to deal with all of these issues. So any system, as you can imagine, that implements process migration will be complex because you have to deal with all sorts of resources. Okay, is that clear? Okay. So now let's go back to this question of network sockets. Okay, what do you do if you move a process that has an active network connection? Okay, process is actively accessing or communicating with another process over a network. Okay, so it has a socket connection open. You move that process from one machine to another. Okay, how do you prevent the sockets from not, or the socket connection from not breaking in this case? Yes.
You forward all the packets, keep the old connection alive, and forward all the packets to a new socket that is bound to the process in the new machine.
Okay, so that's right. So let me just explain what was just mentioned, which was the answer is to forward packets. So the basic point is you cannot move the socket endpoint because it's bound to an IP address, which is basically bound to a machine. Okay, but if you move the process, what you would have to do is basically create what is called a tunnel that basically takes all the packets that are still continuing to arrive on the old socket connection, but then forward a copy of those packets to the new machine. Okay. So we'll set up this tunnel. So when the process sends a packet, it will first go to the old machine, and then the tunnel will then forward that to the other end, which is the other endpoint for the communication. And when packets continue to arrive, they will arrive at the old machine because that's where the socket was opened. They always arrive at the IP address, and then you have to forward them to the new machine. Okay. Now it's a clunky way to deal with it, but that's the only way to deal with it. There is no way to tell unless your process is aware of the fact that it's being migrated. In that case, it can communicate with the other endpoint and say, let's break down the previous connection and establish a new one. But if you want to do this transparently, which means the code doesn't change. When the programmer wrote the code, he or she did not assume that processes are being migrated. When you establish a connection, assume that the connection will stay open. Okay, you don't have to move the processor. If that is your assumption, then you have to implement such a clunky way of implementing a tunnel and forwarding packets, because that's the only option you will have. Yes,
So the old process will have to continue, some portion of the old process will have to continue executing on the old.
Okay, that's a good point, saying will some portion of the process continue executing. Okay, so here is your machine A, OS process, it's machine B, okay, it's OS, this process has moved from here to here. Okay. Packets are coming in. Okay, this is your network interface card. Okay. So the process moved here, who is forwarding the packets? Okay. One option is you do this at the application level where some part of the process stays there and moves it. Okay. That's one way to do it. Or you can tell the OS to do it for you. Okay. Because the process, the packets arrive at the network interface when you set up the tunnel. Okay. The tunnel is basically set up from one machine to another. Okay. So the OS will see the tunnel and it will forward any packets that are arriving on a socket endpoint over the tunnel to the other machine. In that case, the OS can do that for you. So these two options exist. Yes?
If the port is already occupied in the new machine, so what happens in that case?
Okay. If the port is already occupied on the new machine, so when you set up a tunnel, okay, you can bind the old port to any port of the new machine, because that port is not visible to the other endpoint. Machine C that is communicating still thinks it's communicating with this IP address and this port. All the packets are just being forwarded. Okay, so here you don't need to even bind to the same port. If the port is occupied, you can pick any port and say if any packets arriving on port 80 here, go to port 900 here.
But can the port be changed transparently without the process?
Can the port be changed? It requires, so that's a good point. Can the port be changed without the process knowing? It is going to be more clunky, okay, because it is not easy, these issues. Okay, so you will have to basically somehow do it in a transparent manner. Okay, so what the process has is actually a socket descriptor once you open the port. All the port information is stored in the OS because you just simply read or write to a socket once you open the port. Okay, so the process may simply continue to read or write to the socket descriptor. It doesn't actually deal with the port once you've opened it. Okay, so you will do this, but you will not know. Yes.
So, is there any way, like I know this is a bit naive, but is there any way you could actually set up sockets within the operating system itself?
Can you set up sockets within the operating system itself? So sockets are state that the OS maintains on behalf of the process. Okay, all open sockets will actually be, there'll be state for those sockets, there'll be queues for those sockets inside the OS. When packets arrive, they'll be handed off when the process tries to read them. Okay, so there is some work that the OS is doing for you. Okay, because all the packets will arrive at the network interface card, then you'll see what is the socket and you'll put it in the queue, wait for the process to read it and so on.
Right, so like, if that were the case, like if we could just do it all in the operating system, like couldn't the operating system like either set up a new socket or just transfer the information from one operating system to the other?
Okay, so question is, if you are only doing this in the OS, can you not transfer? That's precisely what we are trying to say, that you can transfer it, okay, from this machine to this machine. But the question was, you have to do this for the process to continue to work. Okay, so you will set up a tunnel is essentially being established from one machine to another.
Right. So like you have to set up a tunnel as opposed to just setting up a new socket.
Okay, so question is, do you have to set up a tunnel to set up rather than a socket? It's a fancy way of saying you set up a new socket and just forwarded all the packets. Tunnel is simply a link, a virtual link where the packets are simply flowing.
Right. It just seems like you have to do 3 nodes instead of 2, right? Like instead of just doing it directly from the server to the new operating system.
Yeah, so you will never be able to directly send packets from the sender to this machine because that socket is bound to an IP address. That has not changed. Keep that in mind. Okay, so only the port numbers have changed. You had a question there?
When you write OS, it's actually the hypervisor that's doing all this. You cannot modify. You don't necessarily have to modify the OS. The hypervisor can do that transparently.
Okay. Question is, when you do this, can the hypervisor do this transparently on the OS? When we are talking about process migration, we are not assuming there is virtualization. This is actual process migration in a vanilla operating system. Okay, this was done pre-virtualization, so you would actually have to do it in the OS itself. Okay? If you had a virtualization framework, okay, you could, as you're just rightly pointing out, take advantage of the hypervisor and do additional things to make things transparent for you. There things are much simpler. But you may have to do process migration, as so far we have not assumed that there is any virtualization. So you may have to do this in the OS. In fact, some operating systems that support process migration do exactly that.
So through system calls.
Yes, you have to basically use system calls and the OS interface to do. Okay, so let's continue this a little bit. Okay. So here is another interesting point, which is implicitly when we assume you can move a process or even code for that matter from one machine to another, we assume that the source machine and the target machine are homogeneous. They have the same hardware architecture, same OS. Okay, we have not said you can move from Windows to Linux or x86 to PowerPC, none of that. We assume that migration actually happens in a heterogeneous environment, rather homogeneous environment. Okay. Now you could ask, if you wanted to migrate processes, okay, across machines where the architectures, the hardware architecture of the OS was not the same on the source and the target, could you do it? What would be involved in implementing some migration in that scenario? Okay, so you have a distributed system where machines may be heterogeneous. If you're simply moving a process from one machine to another and the source and the destination are not the same, then what is involved in doing? Okay. So first thing you could say is, as a system designer, that's too complicated. I'm not going to allow it. And that would be a fine choice. I mean, you don't have to, you can always make whatever the right decisions are for the system you're building. Many systems take that approach and say, moving across heterogeneous machine, too complicated, not worth the trouble. Yeah, and so you say you don't do it. That would be the first option. So second option is you could allow it, but then you have to deal with all the problems that come along with it. Yeah, but there are many ways you can get around it in some restricted ways. Okay, so for instance, if you want to move a process, okay, so you can't just, like in the homogeneous case, you can't just move the process and expect it to run. Okay, it will not, especially if even the CPU architecture is different, the instructions that you have compiled don't make any sense anymore. Right? So you can deal with it by saying, I will either translate those instructions before or after. I could do dynamic translation on the fly. Okay, the process will run, but I'll execute the instruction. Or I'll take the code segment. If I have access to the source code, I will recompile that code. Okay, in theory, whether this works in practice, I don't know, because there's lots of things that will go with the system itself. But you could take the code, you could recompile it, create a new code segment for the destination, right, and move that code segment, but then the heap and the stack could move, okay, with the process. Okay. Now that is in some way far more complicated than you can make it. Okay, what you are better off is to do this in a slightly more elegant way, which is, you can say, I will allow this for scripts. For instance, I could write a Python program. Okay, there is nothing that prevents me from moving Python from one platform to another. It's interpreted. Okay, so long as the Python interpreter there, it will run. Okay. So in that scenario, you can allow migration over heterogeneous architecture. You could also do this for platform independent languages like Java. Okay. So long as there's a JVM, you won't care whether it is a Windows box or some other box. Your Java code should run. That's how it's designed to run. A jar file runs on any platform. Right? You're not going to be restricted to platform. So you can actually do this in these more restricted cases. If you are real compiled code, it is much harder or nearly impossible depending on what the differences between the source and the destination architectures or platforms are. Okay, so keep that in mind, saying that when we talk about migration, the implicit assumption is it's homogeneous. Okay? The source and the destination are the same. If they are not the same, you can do it much more easily in this scenario than if you had compiled code where it is more complicated. Yes.
When the interpreting scripts or the Java code, so when we move them, whether it's a strong mobility or weak mobility.
Okay, so question is this, if you move scripts or Java code, is it strong mobility or weak mobility? Is that what you're asking? So typically if it is strong mobility, you're back to this problem because it's a process. Okay, so you can do this much more easily if it's weak mobility. You move the code and restart a new process. Even if it is a Python code, if it's already running, it's a process. Okay, then if you move that process, then it's going to be the same problem because the process won't run, even though the code may run as a new process. Any other questions here? Okay, so if you now ask where, so that's a good discussion to have, but then say where is migration prevalent in today's system? Okay, so we will now talk about a few real use cases and understand how it works. Okay, so in the web, code migration is very prevalent. Okay, lot of HTML pages that you download have JavaScript code embedded in it. Okay, so you downloaded some code, you execute it in the browser. That is weak mobility. The code has migrated from the server to the client. Okay, same with Java applets, Flash pages. In all of those cases, there's some program, okay, and that has actually come to the browser. Browser is executing it. Okay. Another example of weak mobility is batch schedulers for compute clusters. Okay. Has anybody here used Swarm cluster? No. Okay. That doesn't matter. So compute clusters are a set of servers that are designed to execute some batch job on behalf of users. A popular way to use them is to say I need to run some simulation experiments for my research. Okay? And I need lots of machines because there's a lot of computation to do, so I submit a job. Okay? And then the system, and then lots of other users also submit jobs, so there's a queue of jobs. What the system does is it takes the job, first job, and finds a server that is idle and says go run this job. It takes the next job, finds another server, says go run this job, and so on and so forth. So basically you have a queue of incoming jobs, a pool of servers, and there's a job scheduler that's simply assigning jobs to servers. Okay? In this case, the code has been submitted to, so there's something called a head node. The head node is the dispatcher. It's the one deciding which jobs run on which server in the system. Okay? So essentially the head node will take the code that you submitted as a batch job, move it to the target machine, and start executing a process. So it's really code mobility. Okay? Or in most cases, what may happen is you may have a shared file system. Okay, so you don't actually need to move the code. The same files are accessible on all the machines. You simply tell the target saying, go to this file in our network file system and start executing it. So one of those two things has to happen. Okay, but regardless, it's code mobility in some shape or form. Yeah. We'll talk about virtual machine migration on the next slide. So this is another very common use case where not only is a process moving, but the OS and all of its associated process move from one machine to another. Okay, you're taking a virtual machine and are migrating that virtual machine from one system, one physical machine to another. Okay, we'll see a little bit of that on the next slide. And then you have the last use case, not a real use case, but a scenario where code moves is malware and viruses. Okay, that's how viruses spread. Okay, they infect a machine, they put some bad code on that machine, that code runs, it tries to infect some other machine or starts stealing sensitive data and so on. That's an example of code migration as well. Okay, that's how malware actually spreads from one machine to another. Code is jump hopping from one machine to another by exploiting some bug. Okay, so let's talk a little bit about virtual machine migration. Okay. So you know now what virtual machines are. Okay, so in many scenarios, there is a need to move a virtual machine from one physical server to another. Okay. Why do you want to ever do this? So let's say the virtual machine gets overloaded. Okay. Now you can allocate more resources to that virtual machine, but the physical server that is running on may not, let's say, have more RAM, because all of its RAM is used up by other VMs on that server. But some other server may actually have idle memory and idle CPU cycles. So you could take the virtual machine and move it to that other server and execute it there. And then you can give it more resources in that scenario. Now, one way to clearly do it is to shut the virtual machine down. Okay? Take its virtual disk, which is the same as a physical disk, copy that virtual disk from server A to server B, restart the virtual machine, boot it up again. This is the equivalent of I took a server, I took the data on its disk, I copied that data to a new server, I reboot it. The same thing, we're moving a virtual disk by copying it over, reboot the virtual machine. That's one way to move the virtual machine. Another way to move the virtual machine is what is referred to as live migration. In live migration, you move the virtual machine as it is executing. You don't shut it down. Processes will continue to run. And yet you are able to achieve the migration. That is what is shown in the picture here. Okay. So this is showing you a scenario of live migration where the files of the virtual machine are shared, already accessible on both machines, but the memory state is not. Okay. So to migrate a virtual machine, you have to move two things. You have to move the memory state, whatever is in memory, and you have to store whatever is on disk. If you move both of those things over, then you can migrate. Okay. In this case, we are assuming that the disk is shared, so you don't need to move the disk. If the disk was not shared, you would have to move that as well. Okay. But let's see how to move the memory state. Okay. So that picture doesn't show you much, it's just showing that the memory is moving. I'm going to draw another picture here to explain. This is machine A, these are physical machines. Okay. Here is a VM. The VM is, let's say, running OS, there are processes So that's the memory state of the VM. That's what is in memory of that physical server. Okay. Now the disk is shared, so any files that are accessed by this VM will be accessible there. So we're not going to move data. So how do you go about moving memory state? Okay. What you could do is you could take the entire memory one page at a time and just copy it. Okay. So you take the memory, we'll take the first page, first memory page, copy it. Take the second memory page, copy it. Third memory page, copy it. Let's say there are 100 pages to transfer. Okay. You do this sequentially, 100 pages move over. Okay. So now you have a copy of this virtual machine here in this other machine. Okay. But keep in mind that the VM is executing while you are copying memory pages. Okay. What that means is while it's executing, it could modify some of its memory. Okay. A process may run, it may write something to memory, read something to memory. You can start new processes, you can stop applications. So memory contents are constantly changing as the machine continues to execute. So what has moved over here is an outdated version of what is here. Okay. Some of the pages that you moved over may not have changed, but some have changed since you started the copy process. Okay. So what will you do? You will repeat the process. That's the first time around you transferred 100 pages. While you are transferring those, let's say 20 changed during that process. Okay, so in round 2, you will take the remaining 20 and transfer them again. Okay. So you'll basically just cycle back and see what has changed since you transferred it, and then you will say, I'm going to resend those pages. Okay. So you send 20 pages for the second time. While that's happening, the OS is continuing to run, so is the VM, so some more pages may change. Now maybe 5 more pages changed this time. Okay, could be more than 5. I'm just picked, or it could be even more than 20. But the assumption is to transfer 100 pages. Let's say it takes time t. In that time t, some pages change, so you have to basically not transfer those new pages, but those are a subset, so it will take less time. Okay, in that less time, hopefully less pages will change because let's say you're changing at a certain rate. So basically you'll keep doing this in round, and each round hopefully you have to send fewer pages than the previous round because the round is shorter. In that shorter period of time, the OS will hopefully change fewer pages than the previous round. The longer it takes, the more you may change, or more memory may get modified. Okay, so you do this for a few rounds. After a few rounds, you'll be left with a very small number of pages, maybe 5 or 2 pages that you want to transfer. At this point, you will actually pause this virtual machine. Meaning you'll suspend it, move those 2 pages over, or those last few pages over. Okay? So now you have 2 identical copies. Nothing is different at this point because you paused it, so nothing can change. Okay? So since these are mirror copies, you can simply shut this machine down and resume execution there, and you will start exactly where you left off. Okay? It will be completely transparent. Okay? This is how live virtual machine migration actually works. Okay, any questions? Yes.
So the time between pausing that and starting the next one is very negligible.
So that's a good point. So how much time does it take to pause and transfer? So you do that when you have very few pages remaining, so that the pause is in the order of tens of milliseconds, is imperceptible. Okay, so you can't actually tell that anything even happened because it's very small from all practical purposes.
Time to transfer the files is essentially 2 things, right? One is transfer time and another is setting up the connection between 2 machines. So even when there are very few pages, even then there will be some overhead of the second part in it. I mean, I agree.
What is the second part? What are the 2 parts? Can you
setting up the connection between machine A and B to transfer the pages? That will be some constant time, and the other time is actually the number of pages.
Yes.
The time required for each page to get transferred from A to B. So that time is variable depending on the number of pages which have changed.
Yes.
But the second time is constant. I mean, you have to spend that much amount of time at least to transfer the content. Right? So what is the difference in time between these 2 components?
So time to set up a connection is almost negligible because you are on an Ethernet here. Right? So maybe a gigabit Ethernet or some such thing. These are all machines typically on a LAN. So we don't even worry about how much time did it take up to start up a socket connection. most of the time is dominated by transferring memory content. So you may have 8 GB RAM for your VM. That's moving 8 gigabytes of data in the first round, and then any additional data that has changed. Okay, so it's mostly dominated by how many pages you need to transfer. Okay. So basically, in the first round, you will transfer n pages. That's the n is the size of the memory you allocated here. Okay. And then if your dirtying rate is, let's say, r, that's a fraction of pages that are changing per unit time. You'll basically, the next time you will transfer this. And then in that much time, you're going to transfer n over r square and so on. So that fraction keeps shrinking until you reach a small value, and then you will pause and transfer. Okay. But typically, on a good, well-provisioned LAN, this process may take tens of seconds. It may take up to a minute to transfer the virtual machine from one server to another, assuming 8 GB RAM or some reasonable value. And the process is continuing, all the OS and all these processes are continuing to execute. They don't see 1 minute downtime. They see barely a millisecond downtime at the very end. But the whole process may take tens of seconds at least. Any other questions here? Okay, so you have to ask what happens to the IP address of the process or the virtual machine. And move from one machine to another. Okay, so the physical machine has an IP address. This machine has another IP address. Okay, those two are different. Okay, now you moved a VM from one machine to another. What happens? What happens to all the connections that are in the process?
Tunnel.
The process already has a virtualized address. It does not use the physical address anyway. So that way we are saved, but we still have to do the tunneling between the machines as earlier.
Okay, so important point being mentioned here is the physical machine has a IP address. But remember that a virtual machine looks identical to a physical machine in all respects. Okay? Which means it has its own IP address, which is distinct from the IP address of the physical machine. It has its own logical network interface card, a software emulation of Ethernet card, and to that you will assign an IP address. Okay. That is bound to the VM, not to the physical machine. So when you move the virtual machine from here to here, okay, that IP address can also move, meaning that the IP address is bound to the virtual machine. It has nothing to do with the physical machine. It's like you literally unplugged a machine from an Ethernet. Okay? You walked to another room and you plugged it in. The Ethernet card moved with it, so the IP address also moved with it. That's exactly what the scenario we are looking at here. Okay, so the IP address of the physical machine and the virtual machine are distinct. So in this case, the IP address will move. Okay? Now you can ask, so IP address moved, but how is the sender know that now you are on this machine as opposed to that machine? Okay? So the way this works is you don't need to do anything at the networking level. This is handled simply by switches. It is no different from unplugging your Ethernet wire from one switch port and plugging it into another switch port. Yeah, the thing, you don't change the IP address. What actually happens is you have to tell your Ethernet switch saying, I am now on a different port, because what has physically happened is by being here, let's say these two machines are connected to an Ethernet switch. You are now moved from this port on the switch to that port on the switch. Okay. So you basically do what is called an ARP message to tell the post switch saying that I have now, this IP address is now going to show up on a different port. It's like you physically unplugged it and plugged it into a new port. Okay, so nothing has changed from a networking standpoint. All the connections move over. All that you need to do is tell the switch saying any packets that arrive for my IP address, you now send them out on this port rather than that port. And that's it. That's all you need to do. You don't even need to do tunneling. Okay, so it is actually very transparent in many ways. Yes?
The virtual machine migration that we discussed is basically for the type 2 hypervisor, right?
Virtual machine migration, is it type 2? It is
I mean,
type
we
1
discussed.
hypervisor.
Okay, we are so the type 1 hypervisor that we like.
Yes. So type 2 you typically don't do that, desktop thing. So this is typically done in the server world. So you do it in bare metal. You could do it for type 2, there's nothing to prevent it. But most of these are implemented in type 1 hypervisors. Yes, yeah.
So what if you're migrating from, as opposed to something on like the same like LAN network or whatever, if you were doing it like across country?
Okay, that's a good question. So, what if you wanted to do this cross? So this is assuming you're implicitly. Okay, I just assume that you're moving this within a LAN because we are talking about switches and so on. Okay, then the question is what happens if you're doing this cross country? Okay, that is still a research problem. There are people working on this. I can show you some papers that we have written that try to address that problem. It is not as transparent because your IP address, when you move it from one system to another, cannot stay the same, or you have to put in extra effort to keep it the same. So because it's this thing, moving the memory state you can do. It is keeping the networking transparent, which is hard when you try to move it across a LAN, not within a LAN. Okay, so a quick other case study which I already mentioned is, okay, the code mobility is prevalent in malware. That's how malware works. So essentially that's an example of mobile code that is jumping from one machine to another, infecting a machine. Okay, and then you either try to do something malicious on that machine or try to infect other machines by trying to find similar bugs in other machines that are on the network. Okay, so the code is self-propagating. Okay, code sort of propagates itself by trying to infect and inject bad code into other machines. Okay, so it is an example of mobile code or code mobility. Okay, processes are not moving. You put the code into existing process and it starts executing that malware code. Okay. This is, you can have both sender and receiver initiated clearly. So if you know about phishing attacks, okay, if you download something into your mail client and click on it, okay, that is an example of receiver initiated malware. You can have sender initiated malware where you have proactive viruses that look for open ports with buggy software and so on and try to propagate them. So you can get both kinds of malware in this case. Any questions here? I won't talk about how to build viruses or anything like that. Just high-level discussion. Okay, so that brings us to very end of our discussion on processes and threads. There's one set of slides that I had reserved till the very end because this has something to do with the project that you will do when you try to build your client server application for the project. There may be some design issues here, so I sort of pulled that out from the material from earlier lectures and I brought it here. Okay. So for your lab, you are going to do some form of a client server programming. There will be several design decisions you will have to make when you build your client server application. Okay. These are design decisions that are common to any client server application design. So here the first one would be, is your server going to be iterative or is it going to be concurrent? Iterative simply means your server is going to be a single threaded process. It sits in a loop. It listens for a request on a network. Request comes, executes that request, sends back a response, listens for the next request. So it's just sitting in a loop, in a large while loop, just waiting for requests. Each request comes, execute the request, process the request, send back a response, process the next request. It's called an iterative server. Okay. We also talked about concurrent servers. These are multi-threaded servers. Okay. So in this case, there is a master thread that is listening for requests. Okay. When a request comes, you could spawn a new thread and hand that request off to the thread, saying here is a new request, go process it. That thread will process the request. Once the request is done processing, thread will terminate itself. That's one way to write your concurrent process. That is referred to as a thread per request model. For every request, you're starting a new thread. So now you have concurrent processing. Multiple requests can be being processed at once that are coming in by independent threads. Okay. You can also have a request pool where you have a pool of threads. The same dispatcher can find an idle thread in the pool and hand that request to that thread. Okay. That's also an example of a concurrent server. The first design decision you are going to make is, okay, am I writing a single-threaded or a multi-threaded server? Okay. If you write single-threaded server, you cannot handle concurrent requests. They will be queued. Okay. If you write concurrent multi-threaded server, you can handle concurrency. Okay. Second design decision is, how do clients find the server? Okay. So when you have a client process, your server process, they are on separate machines. You'll have to say, how is the client going to communicate with the server? Okay. So simplest answer is you hard code. Okay, you make the server listen on some port number, okay, that you have decided what that port number is, and then you hard code that port number in the client, saying that and the IP address, saying the server is running on this machine with this IP address and this port number. So the client will simply have to then connect to the server. Okay, now clearly, if you start the server on some other machine or some other port number, your client will have to be recompiled. Okay. So another way to do this is to use basically a table lookup, which is called a directory service. In a directory service world, the server will start up on some machine and it will register itself with the directory server, saying, I am server X, or I provide service X, and here is my IP address, here is my port number. So in this case, the client will first connect to the directory server and say, is there service X running somewhere? And the directory service will look up all the services registered with it and say, yes, X is running, here is its IP address, port number. So then you will basically essentially ask the directory server to tell you where the server is running. In this case, you don't hard code anything. You need to know where the directory server is running. Yeah, so you ask the directory server, it tells you, and then you make the connection to the server. Okay. So again, something you will need to figure out. Are you going to do hard coding or are you going to use a directory server? There are well-known directory services that are available to you, such as Port Mapper in Unix or inetd. There's LDAP, which we'll talk about in a few classes. Maybe initially you are okay doing hard coding, but later on you may want to relax those assumptions for your lab assignments. Okay. So those are two key decisions. The third one is your server stateful or stateless? Stateful servers keep state of the clients, keep state on behalf of client. Stateless servers do not keep any state. This client always sends a request, it will process it, it will construct a response and send it back. Okay. When we talk about NFS and HTTP, we will see what stateful and stateless servers mean from a design standpoint and efficiency standpoint. Okay. So, but those are two design decisions. What information does the server keep on behalf of clients? Okay. So let's say if you have a push server, so when the server is pushing data to client, it has to keep track of all the clients that are interested in receiving data from it. That is a stateful server because it has a list of clients that want requests. If you have a pull server, where the clients are actively sending requests and pulling data from the server or asking for some data from the server doesn't need to keep track of which clients are interested. As each request comes in, you process it and you're done. Okay, that's an example of a stateless server where you don't keep track of the state of the clients. Okay, so you may have stateful designs or stateless designs. Okay. Push-based servers are often stateful. Pull-based servers are often stateless, but you could add some soft state for efficiency reasons. Okay. We'll talk about that later on in this course as well, but something I just wanted to explain to you here because there's been immediate implication on what you do for the lab. Okay. Server clusters we already talked about. Okay. In a subsequent lab assignment, not the initial one, whatever client server application you build, you will replicate, meaning you will have multiple servers that provide the same service. Clients can connect to any of the servers and say, process this request for them. Okay. Now you have a clustered server architecture where you have replicated the server. You could have potentially also replicated the data that each server has. Each of those servers may run on a different machine, not the same machine. Okay. Now, so clients can pick a server. Either you could pick the least loaded server or the closest server. You pick some server and say, here is a request, go process it. Okay. So you may have to think about how to replicate subsequently. Okay. And then if you replicate and if any data on one server changes, you have to figure out how the other server will know about it. Yeah, because you can't have new data on one server and old data on another server, because the same request will provide two different answers on two different servers. That you don't want. We want to ensure consistency. Okay, we'll have a fair bit of discussion on consistency later on in this course. Okay, so the very last assignment will require you to do this. At the moment, you don't have the necessary background to do either replication or consistency, but that is coming. Keep that in mind. And also we'll discuss that quite a bit in the lectures as well. Yeah, because clustered servers are very common when you have high volume application, where the number of requests coming in is higher than what a single server can service. Okay, because the server gets overloaded after a point. If there are more requests coming in, the only option is create replicas of your service. Run the server service on more than one server. Okay, we'll do the same thing in the labs as well. Okay. Last part of discussion here is, we know I talked about the sequential architecture, okay, which is iterative, and I talked about concurrent architecture. Okay. And if you remember a few lectures ago, I mentioned the event-based architecture as well. Okay. So I want to talk a little bit about all of these three architectures and have a discussion of pros and cons. Okay. Sequential architecture, serve one request at a time, no concurrency. Okay. Concurrent architectures could be of two kinds, okay, a multi-threaded server or a multi-process server. Okay. In a multi-threaded server, when a request comes in, you start a new thread and you hand that request to that thread. In a multi-process server, when a request comes in, you start a new process and hand the request to the process. Okay. In both of those cases, you can have a pre-spawned pool of threads or a pre-spawned pool of processes. Okay. And when a request comes in, you find either an idle thread or an idle process. Okay. That's a concurrent server. Okay. Now, what is in between is an event-based server where you are using asynchronous non-blocking calls. Okay. When a request comes in, you will basically take the request, start processing it. Maybe it's asking for some data from a file, so you will try to read that data. But you don't make blocking calls. If you do try to read from a file, you typically wait until the results of the read are available. If you use asynchronous I/O, you just hand off the read to the OS and then continue executing. So you can potentially take the next request even before this request has finished and start executing it. Okay. This is referred to as event-based systems. Okay. Where you're using, it is a sequential system. There are no threads, there's only one thread. But you don't make blocking calls. Whenever you have to do any I/O, you issue non-blocking calls and you go back and start processing subsequent requests. When your original I/O has finished, the OS will signal you or interrupt you. At that point, you go back and read the results and send back the response. Okay, so you are never blocked on any I/O. This is how you are going to basically process multiple requests even at work concurrently, even though there is one thread. Okay. So now you have basically a pure sequential model, event-based, thread-based, and a process-based model. And then the question is, if you are designing a server, what are the efficiency considerations for those four types of server? You can write any application or any server using any of those four models. Okay. Which one is most efficient and which one is least efficient? And why? Okay, so that's the part to think about. Any question, thoughts on this? Okay,
If it's for a common service, then it's better if you have a thread-based system.
Okay, so you're saying thread-based. I'm just, yeah, you can have thread-based. I'm just asking for an ordering between those four. So not just you pick one that you like. Yes.
I would say like backwards order, so like process, thread, and then pure sequential.
Okay, process, thread, pure sequential, and event. Where is event?
Well, yeah, in the order you have it there, but
This event would be the top
So let's put the event aside for a moment. Let's take thread-based and process-based. Which of this is more efficient? Thread. Okay, why is it more efficient?
Because it is lightweight and you will not be having to create a separate memory space for every request. That basically the reasons why thread-based processing was used in servers.
Okay. So threads are more lightweight than processes. Switching between threads is more efficient than switching between processes. It all comes down to when you're concurrent server, what is the context switch override? From switching between one thread or one process to another. So switching between threads more efficient than switching between processes. So between these two, there is a clear ordering. Okay? Thread-based wins over process-based. Okay? Now let's take concurrent and sequential, pure sequential. Which one is more efficient? Okay, concurrent will dominate sequential because sequential is just doing blocking. It's doing only one request at a time. Okay, so concurrent can always have higher throughput because you have multiple threads or multiple processing working on multiple requests at a time. So between pure sequential and concurrent, also there is an ordering. This concurrent will always get you better throughput than sequential. Yeah, so that only leaves one, which is event based, and then the question is where does it fall?
During the, when there's an IO intensive jobs are there, then probably, event based would be equivalent to a thread based.
Okay. IO intensive scenarios, they're equal. That's what you're saying. Okay, so that's saying it's a tie. Neither here nor there. Any other thoughts, comments? Okay, so the thing to keep in mind is event-based is also giving you some concurrency by doing non-blocking operation. You can have multiple requests being processed in progress, processing of multiple requests in progress, because you take one request, let's say it wants to do some IO, you do asynchronous IO, while that IO is continuing, you don't block, you go process the next request, and so on. Okay, so concurrency is present both here and here. Here there was no concurrency, so that one is out. So you have both of these can support some form of concurrency. So now what does that mean for efficiency?
The question here would be, what is the cost for context switching between threads and the cost for context for a non-blocking IO call? So while the IO is going on, it's servicing the next request, but when the IO finishes, it will have to suspend processing that request and go back and service the results from the IO. So that would be
That's a good observation. The observation is in a thread base, you're switching between threads. In an event base, you're switching between request processing within the same process. Because then the question is, if there's an interrupt, what is the overhead of switching from the request or processing and go back and take the request of the results of the IO that has finished. Okay? That's a good observation. But what is the overhead of doing that? Okay? So depending on the answer, you will basically be able to order them. Okay? Now keep in mind that in an event-based server, there's only one process. Here, there is one process with multiple threads in that process. So you are continuing to run the same process, but you are switching between threads of the process. Here, there is nothing to switch between. You are simply switching between functions. Okay, interrupt based, when an interrupt comes, you jump to the interrupt handler. You go into the exceptions, exception handling. Like in Java, if you throw an exception, there is no context switch. You just simply jump into the exception handler, start executing that function. So now you should ask the question, is switching between functions cheaper or switching between threads cheaper? Yes, functions is definitely going to be cheaper. There's nothing to switch. You're simply going and making another function call. Okay? So essentially here there is no context switching at all. Okay? You're simply jumping from one function to another, trying to service whatever part of the request remains to be serviced. Okay? Here as you have concurrency, you're switching between threads. So event-based servers tend to be the most efficient in terms of switching. So it is even more efficient than thread-based, right? Except in one scenario. Right? So by definition, if you're single core, event-based will actually beat thread-based. Okay? In fact, the most efficient servers tend to be event-based. If you really want very high volume processing, you'll not even do thread-based, you'll write an event-based server. Okay? The only issue is since this is a single process, if you have 10 or 15 cores, you can't take advantage of the other core. Thread-based servers, you can have real parallelism. Okay? So in a multi-core world, event-based will still run on only one core, single process. Here you will basically start scaling. You could of course write multi-threaded event-based where each thread is doing events on one core. So slightly more complicated architecture. But that's the ordering. In a unicore world, event-based is the most efficient of them. In the multi-core world, basically event-based cannot get the real parallelism, so thread-based will get. Okay, so that's how you will write, depending on what you're writing a server for, that's how you'll make the choice. This is also the most complex to write, okay, because you're actually having to service all sorts of interrupts and exceptions and do non-blocking IOs, a lot more complicated. But it tends to be, to get what you put in. You put in the extra work, you'll get the higher efficiency. Okay. Any question? There's some hand that went up. Yes.
Yeah, that is an event-based service. There should be some amount of state being saved. So if it's servicing request 1 and suddenly there is an IO from request 1, so it will go to request 2. So it will need to save some amount of context of the first request.
So,
So how is it just only a function call? Some state.
so you're saying, why is it not saying the context of that request? The request is already in memory of the process. You think of, there's a buffers where there's a buffer for each request. So when you jump from one to another, whatever work you've done on the request is still in the buffer. You'll come back and you can continue from that point on. So there's nothing to save because you are still in the same process. You're not jumping to another process. Whatever you did for that request is still in the request buffer. Okay. Okay, so let us stop here. We are out of time. We'll continue this next time.